Okay, so last time we left off talking about defects, and we'll pick up on this slide. Again, all the slides are in Box, so if you've forgotten where the link is, you can go back and find it in Canvas, or if you're having issues with computer access, just let me know. I'd be happy to help you out. But before we keep going on lecture slides, does anyone have any questions, comments, questions about final projects or questions about in-class material, anything that people want to chime in on? All right, so again, I've had some email conversations with a few of you talking about different topics for your project or talking about things that you'd like to see in class. Remember, the semester is not close, but the end of the semester is not too far away either, especially with all the other work that you have to do in your classes and research. And so now's the time to start making some plans for November and December so we have a successful end of the semester. And you also learn things that you want to learn. So, you know, that's the point of a graduate elective class like this, is that you get a chance to learn some things that are going to be helpful to you in your current work, or perhaps might expand your horizons a little bit for things you want to learn in the future. So anyway, I'm happy to take requests on material or continue to dialogue projects, and I will give you feedback definitely this weekend, hopefully sooner, on your homework that you turned in. So we've been talking about thermal stresses and defects, which are, you know, they occur in thermal additive processes like material extrusion AM or SLS. But really talking about defects is important in terms of all kinds of different additive, you know, whether it's SLA or whether defects are occurring in material jetting. And so we're kind of going around in a circle here between the different additive processes in these topics, but I think this is a nice way to remind you about the whole spectrum of different AM processes for polymers and composites. So we just don't cover all thermal processes at once and then forget it, and then talk about all chemical or SLA processes or photopolymerization processes later. And we never get back to discussing additive manufacturing sort of as an ecosystem. And I think that's one of the important things that you should remember as you go forward in your career, is that there's a lot of different ways to additive polymers and polymer-based composites. And really the choices that you make for the material, the additive manufacturing technology, the different approaches, those are really driven by the requirements of the application or driven by the goals that you have for whatever you're trying to make. And so in some places, you know, FDM is it. That's all you're going to use. You're going to do material extrusion AM, and that's how they make their parts. And that's fine based on the capabilities of whatever facility you're working in. But if you have a choice between FDM and SLS and material jetting and SLA, then you start to get into the real details of what you need the part to do, what technology can do it, what's the build area, what materials are available. And so integrating all that information is really important when you start to decide what type of additive you want to do and when for what application. So that's why we'll cycle through the additive technologies in the second half of the semester to make sure that you stay on your toes with how the different additive processes relate to one another, and the things that you have to watch out for as you consider all these different aspects of additive. And so we'll switch quickly between the different technologies going forward. And so if I'm not clear on what we're talking about, or if you don't quite remember what SLS is all about, you know, feel free to stop me and say, you know, what process are we talking about? What material are we talking about? Just so we're all on the same page as we work towards a good finish to the semester. So that's why we're cycling back on some of these things. And we're going to talk about defects, and we're going to talk about mechanical structures here in the next couple of weeks. And we'll do a little bit on economics, a little bit on safety, and a little bit on special topics. And so again, if you want to learn specifically about materials in aerospace, or specifically about composites that are going to be used in automotive, or biomedical materials or something like that, feel free to put in your request to me by email, and I'll make sure to include that stuff as we get towards the end of what we're going to study here. Any questions or comments out there? All right, I'm looking at the chat, I think, so if you have anything to say, you can put it in the chat. Otherwise, we'll get started on the slides. So we talked a little bit last time, or we started last time, on defects in printed parts. And so where do the defects occur? How do you find them? Are you going to do CT scanning? What do the defects look like as you build a part, depending on the processing conditions? And so one thing that people would really like to do in advanced additive processing is to find defects as the part is being made. And of course, if you can find the defects as the part is being made, then you have a chance at fixing them in situ, or to have real-time repair of printing defects as the part is built. And so this is just one example from the literature from this paper right here, where they're using stereoscopic imaging, and they're looking at every layer of the part as it's built up, just like you might start to look at every powder bed spread as the part is built up, because every layer in an SLS machine starts with powder spreading, and so you at least have the chance to see, oh, we had a bad spread. Or if you take a picture after the part is written, oh, there was an issue with this certain layer. And so people are working on these things basically right now. We're not going to talk about repair of defects too much, because there's actually almost zero work on that in situ. That's frontier research, and I'm sure people at Penn State are working on their PhDs in terms of real-time repair of defects right now. But at least this gives you a sense for what people are trying. So this image right here is stereoscopic 3D imaging of an FDM, or material extrusion AM part. And this is really cool, because you can imagine a setup like this on a MakerBot that's not too expensive, because cameras are inexpensive. It turns out that stereoscopic imaging software is not that expensive either, and there's a lot of free stuff out there. And so if you get this set up just right, now you can start to build up what might be a virtually printed part, or a measured part as it's being built, versus the CAD model. And then you can start to look at the detected geometry, and where you have deviations in detected geometry, that's of course where the defects are. So in this scheme of 3D printing, where you're building up layer by layer by layer, of course, any deviations in layer height, any strange things going on with geometry are going to tend to show the presence of defects. And so that's how, in this paper, if you read it in detail, that's how they find defects. And then, of course, you can CT scan this object, or you can do mechanical testing on this object, and then look at the fracture cross-section. You say, oh yeah, the defect caused the mechanical failure. And this is not so exciting, because it's just a block of material. But you can imagine, as the structure gets more and more intricate, you'd really like to have this information, including what are the dimensions of the printed object as it's being printed. Because we all know from other additive classes and in our discussion in this class, that just because your CAD model gives you a certain set of dimensions doesn't mean you get exactly those dimensions when you print the object. And so being able to measure dimensions in real time has a lot of utility, and people are continuing to work on it. Any questions, clarifications, any more discussion on this specific paper or approach? Okay. If you've worked with industrial printers, some of this stuff is starting to be incorporated into industrial printers. Things like cameras, things like dimensional laser scanning. So Markforged has a laser scanning head on it, so you can pause the print, you can laser scan the layer, and then you can restart the print. And so this is making it into industrial additive, although it's not very common yet. We talked a little bit about SLA defects, and there's a lot of how-to online for SLA defects. And one of the ways that SLA defects can really become important is because in most SLA processes, you're going to have some pulling force on the part. That pulling force can create defects if you have bridge structures or if you have overhang structures. And so this is a nice paper that goes into this idea of what is the force on the part as you're printing due to this pull-off mechanism. So we saw this in Formlabs. They have a lot of IP on how you might release the part from the window. Of course, in a carbon printer, this is not going to matter as much because it's a continuous elevation of the part. However, there's still mechanical stresses on the part. And so even if you have continuous elevation of this build platform, you know, there's still going to be forces on printed part during elevation. So this can introduce defects, and this has to be analyzed. And of course, you can change the print orientation, you can change the design of your part, you can change the support structures, but these are things to think about, and this can cause problems if you want to 3D print something that's not going to be able to withstand these stresses. And so they talk about cantilevers and overhangs and some of the considerations for this pulling force. The other cool paper that I found is doesn't have anything to do with the defect during 3D printing, but they're making materials with defects in them to get insights into mechanical properties. So this is basically using a 3D printer to make a defective material purposely to study the mechanical behavior of that. So this is a paper that was written in England. You can tell by the spelling of behavior right here. And I think, I don't have the DOI number on here, but if you just Google that title, you'll be able to find it. But basically, this is a cool use of 3D printing because they have a real sample. So it's actually a piece of volcanic rock that they drilled a core out of. And so they can scan it with CT scanning. And micro CT is not any different than CT. It's just at high resolution. And then they can create a digital model of a rock. And instead of breaking this volcanic rock specimen, which is very expensive to get because you have to go to a volcano, then you have to drill a core, and that takes time and money. You might just want to make a reproduction of that rock from your digital model, and then you print it, and now you have a replicated 3D printed rock that you can test this. Now, of course, it's not rock, it's plastic. And so this is not going to be perfect, but it can allow you to evaluate what's the effect of all the porosity in here, what's the effect of any cracks that you might be able to see in the CT without having to sacrifice the real specimen. And so this is being used a lot for failure analysis or engineering analysis of parts that you don't want to do destructive testing on, because some parts, like this volcanic rock sample, are irreplaceable. You can't break it, or you don't want to break it. You can't do destructive testing of that sample. But you can replicate that, albeit not in volcanic rock, but in plastic. You can replicate that, and then you can easily do destructive testing of this thing because you can just print another one based on the model. And this, like I said, this is being used a lot in engineering analysis, or if you have an old part off of an airplane and you really don't want to test it destructively, you want to keep that part intact, you just replicate it with a CT scanner, get your new 3D reconstruction, and then go ahead and print some new parts in metal or plastic or whatever you want. So this is not studying defects in 3D printing. This is studying defects in materials using additive manufacturing as a tool. So I just came across this paper. I thought I'd share it with you all because it's interesting. I'll pause here for questions or comments. Anyone who wants to chime in or bring up something for the benefit of the class? Okay, so if there's more things on defects that you want to hear about, I mean, we've been talking about defects since we talked about interlayer adhesion and road adhesion and things like this, because of course, additively manufactured parts are filled with defects, but finding them, fixing them, controlling them is the hard part. But if you want to hear more about defects or what people are doing in defects, just let me know. But that's about all I have for you on specific defects in additive manufacturing. And defects really fall under this umbrella of quality. So Deloitte, which is a consulting firm on lots of different stuff, but they have an additive manufacturing arm, and they've done some really nice analysis of the additive manufacturing industry. They've done some really interesting analysis of technology uptake for additive manufacturing. And you'll see in the second half of the course, we're going to discuss a couple of these Deloitte reports because they have a nice framework to understand systematically what you might be interested in as you try and industrialize additive manufacturing in your own company or in your own manufacturing facility. And so defects relate to the quality of a part. And if you've ever worked in a company or on a manufacturing line where you're making tens or hundreds of the same thing or millions of the same thing, you know that quality is really important, and controlling defects is part of quality. And so the first facet of AM quality, at least according to this Deloitte model, is that you want repeatable quality with the same printer, materials, operators. So if you have 5 people standing in 5 different, standing in front of 5 different printers, can you get the same part from all those operators and all those printers over and over and over? And so that's a challenge already. I know that lots of you don't print the same part over and over and over, but the printer changes. Also, in the second facet of quality, you see under any set of environmental conditions. So the temperature goes up and down. And when the temperature goes up and down in our lab, the printing changes a little bit. And so that's important to remember. And so how do you guarantee quality as conditions are changing? In injection molding, since it's an enclosed environment, you dry the polymer. There's other ways that the polymer industry has tried to control quality. That's important. You'd really like to have quality without any direct input on tweaking the part or without changing things as the environment changes. That's important. And then figuring out when you deviate from your quality envelope and what to do about it. These are all the facets of AM that you should be interested if you're really interested in quality and controlling defects. And so it's okay to have defects. You know, they say ensure repeatable quality. So they don't say ensure maximum quality, because in industrial manufacturing, defects are tolerable as long as you can design around them, or as long as your part performance can tolerate defects, because having no defects is extremely expensive and unrealistic in a manufacturing environment. And so ensuring repeatable quality really means ensuring repeatable defects and knowing what the defects are and controlling those defects to the same level in every part, not having zero defects. And so that's an interesting thing to think about for those of you that haven't worked in a manufacturing facility. Not everything's perfect. You know, it has to look pretty good to the consumer, but in all quality assurance, quality control testing, there's a band of acceptable quality, and you just need to stay within that band. Not everything's perfect. And so this is something to think about as you think about what would it really take to deploy additive manufacturing for hearing aids or for automobiles or for cell phones or something else. And if you ever work in an industrial facility, you'll hear a lot about quality, including standards, ISO standards and things like that. And so there's a lot of this discussion about quality control in AM. And so because additive manufacturing is basically a new industrial processing method, figuring out what the rubric or framework is for how to do quality control in AM is really important. And so these are just some references. You can look at this. We're not going to go deep into, say, standards quality control and measurement sciences, or what IBM has to say about Internet of Things and quality control. But these are some references to help you in the future if you dig into this quality issue. Any questions on this? All right, that is lecture 10. And so if you go back to the box, I think we're on lecture 11, if I can find it. There we go. All right, so lecture 11 is going to be about structures, and we're going to talk about that in a second. But now that we can make 3D printed parts, understand the materials, understand the process, understand how to make composites, you know, we've really built up a lot of information about what additive manufacturing is and what materials in terms of polymers and composites are possible in additive manufacturing. Now we're going to talk about what we can do with it and some of the unique structural tools that people use to understand additive for sort of next generation applications. And we'll go through specific units on automotive, aerospace, biomed. We'll talk about some more examples in those application areas, which is where additive is really taking off. But I wanted to do something on structures and eventually 4D printing so we can see what the frontier looks like in terms of new things that are enabled with additive. So before we do that, we'll go back. I just wanted to talk about this a little bit more. You've seen these Oak Ridge bars. We've talked about this twice already. And we know that there's an issue with getting good properties out of this big area additive manufacturing process with this composite. And the key to getting good properties is sorry about that. Oh, we'll see if my computer comes back here. Oh, bear with me, I might have to close my PowerPoint and open it again. All right. There we go. So in order to get good properties in these dog bones, we need good road adhesion. And we need to understand time and temperature, because time and temperature determine molecular diffusion across the interface, which we need for road adhesion. So this is all wrapped up together, and we've talked a lot about viscosity. We've talked a lot about time temperature superposition. We've talked a lot about molecular diffusion across the interface. And so in order to understand why there's this gap between 3D printed materials and the spec, developing a thermal model is one of the ways towards that. And so we saw the thermal model for polymer welding that Joe Bartolai and Tim Simpson have worked on, really studying that molecular diffusion and figuring out how that works. And the Oak Ridge folks also have a thermal model for their big area additive manufacturing process, where now they're able to build up for different layers. They're able to build up this temperature as a function of position and time. So they know what the thermal history is for the build. And from the thermal history, you can determine how well roads are adhered, and things like thermal stress and all the rest. And this is in this Society of Professional Automotive Engineers preprint. And so you can check this out, because when you develop this thermal model, and this is just showing the local model right here, but validating what the model versus experiment looks like if you're measuring the temperature, you can try and extend this to the whole BAM machine. And of course, the big area additive manufacturing machine is big. It's like 3 feet by 6 feet by 3 feet. You have the model of your car, the Stratty that you want printed. You have a mesh for that car for the different finite elements, and you can run your thermal model. And it's really a thermal mechanical model. And you can figure out where the stresses are in the car. So this is really cool, because this gives you now a way to evaluate the residual stress. It gives you a way to evaluate deformation. But the upshot is that this model had to be developed from scratch for this printer, for this model, for this toolpath. And so we haven't talked a lot about how different models require different toolpaths, but toolpath is just how the model is traced as a function of time, layer by layer. And so you can learn about that in other additive courses. But depending on the toolpath, or depending on the path which the head takes, of course, that's going to give different parts of the car different thermal histories. And so that's going to cause different residual stresses and different deformations. Now, they don't have a line, or they don't have the code for determining the strength of the weld like Joe Bartolai and Tim Simpson do. That's a little bit different type of model than this model, but at least this now gives the people printing these large structures what multi-scale failure mechanisms might look like based on the residual stress, where the deformation is based on the strength of the material, and trying to figure out, what's a good way to print this car versus what, might not work. And so this all helps in trying to figure out the best way to print this structure based on all the thermal inputs. And I told you the story about when they printed the car slowly, they got a lot of delamination. The car was too cool. They couldn't get anything to stick together. So when they printed it faster, it actually had better adhesion. And so they were able to demonstrate that. But now they can really understand this full thermal model and all the things going on. And this type of activity is being done for other industrial 3D printers. There's some open source code out there. This is being done for SLS as well. But this is sort of the forefront research in terms of how do you go through the whole process in the computer so you can figure out the best way to do the build before you build it, because this is hundreds of pounds of expensive polymer and hundreds of dollars an hour to operate the machine. So you'd really like to have a good idea of what this is going to look like before you make the part. And this is how modern manufacturing works in terms of injection molding. So there's mold flow and cooling analysis. Or if you're going to do another type of industrial processing like casting, there are good models for that. And so this is really trying to use modern manufacturing tools to do what might be called digital manufacturing. Before you go to the real thing. So that's just an aside that I found in a little bit of additional research, so I wanted to bring that up. Now, just because you have this digital manufacturing model doesn't mean you can necessarily mitigate some of these problems. You know, you still might have this gap in properties and nothing's going to allow you to overcome that gap, but now at least you can understand where these failures might occur and where the weak parts in your car might be, and you might be able to design or plan around that in terms of what your toolpath generation is. And so sometimes you just have defects that you can't overcome, but as long as those defects are predictable and controllable, you can still design a part with defects. A lot of the times we work on polymers, and the engineers would say, you know, I just need to know what the properties are because I can design a fuel cell around the properties of this polymer. But if your properties are changing, I can't do the right type of design. And so even though you might have a material that doesn't meet the spec you want, you can always design around knowable defects. It's really the uncontrolled defects that are the big problem. And so in this idea of digital manufacturing, you can really figure out the best way to do things given the material properties and given the shortcomings of the process that you have. Okay, I hope that's clear, and that sort of wraps up the story in terms of you know, talking about these tensile bars and all the things going on in polymers versus composites at large scale. And there's a lot of interesting information if you're really into big area additive manufacturing, or you want to think more about this large scale 3D printing. There's always good stuff coming out of Oak Ridge. And so I suggest you check that out, and we can continue to discuss it if you have specific things you want to talk about. Any questions or comments? All right. So this idea, we've seen this before, and I bring this up just because if we're going to talk about structures, usually you want things that are light and strong. And so you can see here for all different lattices and foams compared to technical ceramics, and this is from this paper that you've seen before from Professor Lewis. You know, really the goal is to come up with structures that give you light or low density, and strong, or in this case, high elastic modulus. So this is what we might call an Ashby type plot, where you'd really like materials that are up in this quadrant, but there seems to be some sort of relationship on the diagonal here, and this goes up and down depending on what the material is. But it turns out that lots of things that are foams or lattices tend to lie along this limit. And so that's an important learning if you're going to design structures. You know, that's why bridge trusses are lattices, or that's why we put foam in a sandwich composite, so we can have something that's both light and strong depending on how that composite is built. And so this is a interesting example that we've seen before. And I just wanted to remind you of the goal for what, if you're going to design a structure, what you might be interested in. And there's a lot of cool things out there in terms of, rather than making a lattice like this object right here, and we'll talk about different types of lattices, you can start to think about what's in those lattices. And so in these tendons of the lattice, Professor Lewis used this foam, but they also did this really nice demonstration where now they have core shell filaments. And so there's a flexible core and a brittle shell. And the brittle shell gives you strength. So you have a nice brittle epoxy. So this is high strength because it's going to be high load, but it's brittle because it doesn't have very much displacement. And so brittle, it turns out, is a technical word, just like tough. And so a tough material has large elongation to break, and a brittle material will have low elongation to break. But brittle and tough don't say anything about the strength. And so you have high strength materials versus low strength materials. And of course, the toughness is the integral under the curve. And so you can compare those two things. But anyway, these sort of composite filaments, or this sort of mixing of flexible and brittle materials, can really allow you to tune the toughness based on what your application is, or allows you to tune the mechanical properties. And so they made these nice lattices, right here, out of these core shell filaments. And so they were able to get, with brittle epoxy versus core shell filaments versus having a nice interfacial material, you can see this long failure curve that looks flexible, but if you look right here, this is higher initial strength than flex. And in fact, it has a higher strength overall than if you just use flexible. Because you might say, well, I just want a tough material. Give me something that's really flexible. But flexible materials are not going to have this initial strength. And so at low strain, using this core shell approach, you still are able to carry these high loads. And it's only when you really start to push on this and you start to break this lattice as you go 1, 2, 3, having this composite behavior of both high strength plus it fails gracefully over a long displacement might hold some advantages to having just a purely hard material or a brittle epoxy that fails right away, or this flexible epoxy that's just too squishy, especially at low deformation. So this now gives you some sense for how we might combine the filament morphology with the macroscopic structures in order to obtain mechanical properties that are not easy to obtain from a single material or from just a solid block of material. And so this really gets into the area of architected materials. And this is something that's interesting in additive manufacturing, because in additive, of course, we can make structures that are really hard to make otherwise. It's really hard to injection mold a mesh that looks like this, especially at this length scale. So that's cool. And that's one level of architecting. That might be called the millimeter scale or the macroscopic architecting of a material. But then you have the chance to do the microscopic architecting as well. These core shell filaments are composites in and of themselves, and having the core shell with a designed interface has properties that you can't get out of a single material. And so now we have architecting at a different level where the filament itself is architected. And so we might call these multi-scale architected. Oh, let me get rid of this thing. Or multi-scale materials, or you hear lots of different nomenclature for this. But this is how some of the most outstanding materials work in nature. We might call this hierarchical assembled materials or something like that. So things like nacre, things like bone, things like skin, they have a multi-scale architecture of sometimes it's different materials, sometimes it's a composite, but this is really how we get light and strong materials with outstanding properties that we just can't get from a single block of material. Any questions or comments on that? Okay, and this is where additive gets interesting because of course these are hard to make by other ways, but also additive is an interdisciplinary field. So you need mechanical engineers, you need chemists, you need material scientists, you need a bunch of different experts in order to really take advantage of everything that additive has to offer. And these sorts of innovations are coming into industrial applications, whether it's advanced crumple zones in cars, or whether it's personal care goods or soft touch goods for people that have different properties. And so people, like to interface with other soft and squishy things. Say if it's a robot, like a housekeeping robot or something like that, these sorts of advanced materials ideas are making it into advanced applications or medical devices or something like that. This is another really cool demonstration from this science paper right here. And I think this is the group from Lawrence Livermore National Lab. And so if you're interested in additive manufacturing, you should have Lawrence Livermore National Lab on your radar screen because they're doing some of the coolest stuff. And they have these two types of trusses. And so they have what's called a stretch dominated truss. Yeah, so that's A. So this stretch dominated octet truss is A. And then they have these octet truss unit cell. What? No, hold on. Not that. That's not the one. This is the one right here. This is a bend dominated decahedron type unit cell. So you can see that the octet truss, which is usually what we think about when we think of trusses, right? We think of triangles put together in such a way. What's interesting about that design is it's a stretch dominated unit cell when you deform it. And so you have members in tension and compression. And so this really works well for steel because, of course, steel is good in tension and compression. And that's why bridges tend to have this triangular form. So this other decahedron-based truss is interesting because it's got a lot of bending moments. And so rather than stretching or compressing along the tendons of the truss, you have all of this bending. And that might not make a lot of sense initially if you haven't studied mechanical engineering or you've never had a statics course. But what you need to know is that basically these trusses fail in different ways. And so people are really interested in using this architecting or the design of the materials or the macrostructure of the materials in order to do different stuff. And then you could think about what are the trusses made out of? You can't read that. I can barely read that. Let me try that again. My pen's working here. What are the trusses made from, and what is the internal structure? So going back to this idea of a hierarchy of material design, maybe the trusses are core shell, or as you'll see, the trusses will be hollow in one of these cases. And how does that roll up into the macro scale structure? So very similar type of idea as to this paper right here. And of course, making these things, now these are really small. I think these were likely made on something called a nanoscribe. Or they were made using micro stereolithography. And so you get these small structures and you can test their mechanical properties. Oh, hold on, I have a chat. Sorry, I missed that one. Is there a reason? Okay, so everyone can read this chat if you pull it up. And the question from Jivtesh is there a reason these composite structures are often mentioned in strength mass scenarios for energy absorption and lightweight parts? How do these materials perform under fatigue? Would adhesion between soft and rubbery materials be of significance? Yeah, so adhesion is important because they show that the interface, so as you design the interface between the core and the shell, that matters. And then the fatigue properties of architected materials can be different. We'll show some recovery curves, but that's a different sort of analysis than just this light and strong Ashby type plot. So fatigue, interfaces, all of those things that Jivtesh brings up are important. And the key is, what is the application? What are the requirements? And what sort of materials do you want to demonstrate these relationships on? Of course, we're not worried about core shell adhesion if we're using foam because there is no real core shell here, but we might really care about the fatigue properties of these things. And so fatigue, you'll see, we'll see some hysteresis curves where we load them and unload them. Basically, these trusses or these meshes are just stress strain tested once, but you'll often see fatigue curves. And so architected materials can have different fatigue behavior than the solid form materials that we're used to seeing. So these points that Jivtesh brings up is good to keep in mind, and it matters for sure. Good question. Okay, so going back to what the loading looks like and what the truss looks like. So what they do, so they're not using nanoscribe, they're using micro stereolithography, and so we can call this micro. And basically, that just uses this projection lens to make a part much smaller than we would in, say, a regular stereolithography setup where we have a larger lens. Oh, I see another question. I wanted to know if there's a significant disadvantage or unpredictability. So just like everything in processing of materials, it depends. So if you don't have a good interface between your core shell filament, you won't get the type of performance that you really would like to in terms of toughness. Now, that isn't necessarily unpredictability because you can predict, if I have a bad interface, I'm going to get bad performance. But if you're interested in architected materials, you do have a lot more interfaces in here. And so you do have the chance to have more defects. You do have the chance, if you don't fuse these filaments just right and you start to have a defect in your lattice, that can introduce unpredictability. But it's really when we're talking about building up the fundamentals, there's no such thing as advantages or disadvantages. It's just the performance that you want. How might you get it in terms of, is this blue curve better than the red curve? Well, it depends on the application. Or maybe you want something that's brittle and is going to be really strong but fails all at once. But the unpredictability can really come from the control of your additive process. So again, since this is research, of course, it depends. But I think the tools that we've discussed in terms of defects, in terms of if there's issues at interfaces, that can all lead to lower performance than you might desire. And that puts you off some of the limiting behavior of a curve like this. All right, good. Thanks, Jiptesh. Yeah, and if you have more questions, feel free to type them in the chat. Hopefully I'll see them. But anyway, these trusses, rather than being made with a nanoscribe, we can put versus micro stereolithography. So that's something to remember, is that you can still make some pretty small stuff using this, using these techniques. So what they did was they made a polymer part. So this is polymer, photopolymer SLA, just like we talked about. They're going to coat it in metal. Then they're going to dissolve away the metal, and they're going to get a hollow metal structure. So that's cool. And this gets to the idea that you can have architected trusses themselves. And so they say, whoops. So they say that the edge of this truss is 40 nanometers and it's a hollow tube, but you still have a truss that looks like figure C here. So this hollow tube metallic nickel phosphide truss is really interesting, and they demonstrate that you can make a hollow tube ceramic truss or a solid ceramic truss if you want, depending on what processing you do. So that gets really interesting now for making these trusses out of different materials, different architectures, and of course you have the macroscopic architecture, whether it's this bending truss or this axial stress truss. And so as you look at different relative compressive stiffnesses versus relative density, so it's just a way to normalize based on the material properties, you see that the octet trusses, and they call these now Kelvin foam, so that's just the person who analyzed the mechanical properties of that. You see different relationships now between the density and the strength, and maybe these all fall along the same diagonal lines, but they occupy different parts of the diagram, where now, depending on the needs of the application, you can really design in the structure and complement that with whatever material you want. So whether it's a stretch dominated lattice or a bending dominated lattice, and whether it's made out of solid material or hollow material, this gives you the span of properties that's possible. And you notice that we've got 1, 2, 3.5 orders of magnitude in relative density, and we've got 1, 2, 3, 4, 5 orders of magnitude of compressive strength difference. And so now you can get a huge variety of properties just by shaping these materials differently. And that's really one of the magic parts of additive manufacturing, is you can just get much different types of properties than you could by just selecting different materials. And so they show this on the Ashby plot. Metals, technical ceramics, composites, elastomers, these are conventional materials, and they all sort of lie up here. And you see these are all relatively high density, because compared to these open scale trusses, a chunk of metal is going to be a lot heavier or a lot more dense in terms of the overall bulk density than some of these trusses. And you can go to really low density with some of these materials while still maintaining reasonable strength. So of course, if you need strength up here in hundreds of gigapascals, you're not going to be able to use a truss. But if you're really sensitive to density, if you want really light materials, say for space or for portable applications where things need to be as light as possible, you're not going to be able to get a solid metal or a solid plastic even that's light enough. You're going to have to rely on this material architecting to still maintain some sort of Young's modulus that you can design around while still getting really, really light materials. And the theory for this has been known for a while. Ashby is one of the fathers of mechanics of materials, and he was a material science professor in England. And so this is not that old of an idea, but until we had really good additive manufacturing and until we could make some of these hierarchical structures and test them in a reasonable way, we could never get these really light materials. And sometimes you see papers on aerogels. Sometimes you see papers. There was a really cool one where they took this metal truss and they set it on top of a dandelion that was about ready to lose its seeds. And so this piece of metal was just sitting on top of a dandelion without deforming it. That was really cool. So things that are ultra light, materials with ultra low density. And of course, if you make this out of ceramic, you now have a heat resistant tile, like the type of tiles that they use on spaceships, where the ceramic provides the thermal properties, but it's ultra, ultra light and traps a lot of air. And so it has really good insulative or low heat conduction properties as well. So there's all sorts of uses for these types of architecture materials, aside from just making things light and strong. Any questions on this? Okay, and so I don't want to give you necessarily the impression that only additive manufacturing can do this. Foams, aerogels, xerogels, all those sorts of things people have worked on for a long time. And so if you're interested in looking into those, even people 3D printing with aerogels and xerogels is coming out. And so again, that's now a hierarchical material where you can adjust the macro scale and the micro scale and get whatever customized properties you want. Another way that this is done, for those of you that are not interested in electroplating, but you can put the nickel precursor right in your SLA bath. And so this is a really nice paper if you want to check it out, because it shows you all the different types of stuff that you could put into an SLA resin. So you have your acrylate crosslinker, you have your photo initiator, and what they use, which is really cool, is they use this nickel acrylate complex. So nickel 2 plus is an ion, and of course, when you reduce this thing with a chemical reduction agent, or they do it with pyrolysis, so this is thermal reduction, you're going to get nickel 0 or nickel metal. And so you basically put this salt into your SLA resin, and then you can reduce the salt thermally. And we saw this a little bit when we were putting silver nanoparticles in our material, and we were getting the reduction based on a radical reduction of the silver salt. This is a little bit different. You print this structure using bottom-up SLA, and they provide a nice diagram for that. You wind up with something on the order of 10 microns for your nickel salt containing SLA printed resin. You thermally reduce it, so you pyrolyze this probably under nitrogen with a little bit of hydrogen to get a reduction. You get shrinkage because you've gotten rid of all the polymer, but now you have fused nickel-based metal that you can look at in terms of its properties. And what's interesting is that they show diagrams of the precursor. And so you can see all those little specks in there, that's all the nickel salt. And when you reduce it, basically you have all these fused grains of metal after pyrolysis. So rather than electroplating the structure and making it hollow, so you coat the surface with metal and then you just dissolve the polymer away. Basically, you transform the polymer containing a metal salt into a pure metal, so you get this grainy type structure. Now that can introduce defects, but it might also have some advantages because those trusses might be a little bit stronger, or they might have higher surface area, which you're interested in. But basically, this paper is just highlighting all the different possibilities, or one of the different possibilities that you can use for a custom SLA resin that you can do post-processing of to get something else. And so in this case, they're looking at the fatigue and recovery properties, or they're looking at the loading to failure properties. I guess this one isn't fatigue, but we'll get to fatigue in a second, where now they have reasonable specific strengths at ultra low density, ultra low beam size versus some of the conventional materials using electron beam melting or selective layer melting or some other metal processing. So compared to different types of metals or different ways to do this, they're showing some advantages in terms of the size of the tendons versus a specific strength. So whether or not those mechanical properties are important, that's up to the application, but this is a nice demonstration of customized SLA resins to do something really interesting. So this paper gets to this really interesting idea that Jivtesh brought up about hysteresis. So say you have a truss type structure, and I don't know why I don't have a picture of this. Oh, I am going to have a picture of it in a second. But say you have a truss like this, and you start to compress and unload, compress and unload. I mean, a bridge that's built out of trusses goes through this cycling as well. It just doesn't compress very far or doesn't deform very far. But you do see wind loading on bridges building, skyscrapers will sway back and forth, bridges will sway back and forth in the wind, and they're designed to undergo this hysteresis. And the question is, can you get really interesting stress strain properties? So this is out to 25% deformation. And can you get recovery almost back to zero? Of course, you'd really like your skyscraper or your bridge to go perfectly back to where it was, but this is now pushing the limits of these hierarchical, they call them metamaterials. I tend to call them architected materials, but a metamaterial is fine because you can have mechanical metamaterials, which is just gets across the idea that it's not a bulk material, it's an architected material. So there's lots of different words that people call these things, but you'll see metamaterials out there, and there's thermal metamaterials, there's electrical metamaterials, there's RF metamaterials, but they all rely on this architecting depending on what your goal is. And so this paper right here shows that you can really deform these trusses depending on how the lattice is made versus things that are more random foams. So of course, foams are light materials, but by architecting in terms of lattices, you can start to get significantly higher tensile strains and still have good mechanical strength that you really just can't achieve with the elastic limit of foams where they just come back. And so the mechanical properties, or the samples and the mechanical properties, look like this, where now you have these really interesting lattice structures and you're going to compress them. And so what happens is that based on the deformation, and this is a good line to look at right here, based on the deformation where you're going to squeeze this truss, it deforms differently in different parts of the structure. So some parts stretch, some parts compress, and then that's what gives you these high strains where you have, in essence, graceful failure rather than everything going to pieces all at once. And so this idea where now you can control the deformation of the structure depending on how you print it is very interesting because you're not stuck with the same thing over and over. And so we're going to talk about some very specific cases of designing deformation of structures, which is the idea of architecting materials, or is the idea of mechanical metamaterials. Any questions on this? Okay, so again, for people who are chemists or people who are material scientists that haven't taken their mechanics courses yet, you know, this might seem a little bit esoteric, but this is useful because this shows you the real power of additive rather than just making, you know, some plastic component or something like that. So this is really at the front lines of how some of these new additive products are being developed. And so this gets pretty real when you're interested in designing shoes or you're interested in designing football helmets. So if you look at Carbon's architected foam, that architected foam is in their Futurecraft 4D shoes, and it's also in their Rydell football helmets. And so this is worthwhile paying attention to because this is how the latest generation of products are being designed. Okay, any further questions? All right, we just have one or two more slides to show some specific examples, but I wanted to show this really awesome video of micro stereolithography because it shows you basically all the things that they did to print this truss. So this is a nice video. Let me see if it plays here. Okay, so that's the design. We know that. Okay. So this is microstereolithography, and it's no different than what we talked about before, but it's got this lens in order to compress the light source. So you see the light source right here, or this is the image of what they're printing. And so in regular stereolithography, you have some focusing lenses in order to get the right focal plane and everything else. But microstereolithography will tend to be done through one of these zoom lenses, so you can get very small feature sizes. Of course, you can only print very small things in microstereolithography, but this is worth thinking about how you get these small structures. And this video is cool because they're showing vat polymerization from the top down, and it's showing you how the part is built up because it's all nice and clear. It's great. It's a nice video. And they pull the part out. Okay, So notice what they did right there. So they designed this truss right here. So just looks like your normal truss, right? When they were printing it, I mean, the printing is very cool, and out it comes. That's great. And this looks like just a block of um, of foam or whatever. I mean, we don't even know it's elastic yet, but this could be done in sort of any SLA environment. But if you look at the key properties of this thing after it's all done, it looks like this is washed and post-cured. This is pretty nice. It's an elastomer. What's special about this architected material is it's flexible in one direction, but it's rigid in the other direction. And that's key to getting advanced properties. So this is unusual behavior, and I'll just play the rest of the video right here. So it's flexible, and then it's rigid, all based on the design of that truss. Great. Yeah. Oh, let me stop that.
I feel like we're.
So that's cool. If this comes back. So that's really interesting because now you can get material behavior that you wouldn't necessarily get from a foam. So it's really hard to make an elastic foam that has that anisotropic mechanical properties. And so that's one of the powers of architected materials. And I have one more thing to show you if I can get my PowerPoint moving in the right direction. Oh, maybe not. Maybe we'll go back to YouTube for the last video. And so this gets to the issue of how do you design a structure with a certain material to do new things that the materials can't do themselves. And so is it, well, let me do this one. So in this video, this structure has what's called a negative Poisson's ratio. And if you're not familiar with what Poisson's ratio is, it basically, Poisson's ratio says when you squish something, it squishes out the sides. So you take some silly putty, you squish it down flat, and it leaks out the sides. And that's the Poisson's ratio of the material because you have conservation of volume. So that's pretty reasonable. But with architecting, you can design in a negative Poisson's ratio. So what's going to be shown in this video is that you squeeze this material down and the sides are actually going to draw in rather than squish out. And so let me play this and you can think about this and do some of your own YouTube sleuthing this weekend. So here goes. Come on. So we're squeezing down. If you hold your fingers on the side of the screen, you can see that even though we're deforming this material in the z-axis, it's pulling in the x-axis, and it's a very short video. So we're squeezing it down and it's pulling in, and that behavior is called a negative Poisson's ratio. Very few materials do that, but with 3D printing, you can make metamaterials that have an internal structure that deform in very specific ways in order to architect in this negative Poisson's ratio. So using polymers and composites, we're going to talk about some of these different structures, and I'm going to show you a couple papers that if you're interested in the architecture of the part, this will help you think about what's possible where now you combine materials and you combine the shape of the object to get new properties in this area of metamaterials. So are there any questions or any comments here as we wrap up class? All right, so we'll talk more about this next lecture. And like I said, whether you're a chemist or a mechanical engineer or an electrical engineer, you know, there's something in this for everyone because this now gives us access to material properties that you just can't get by looking in the book and finding the right grade of polyethylene or finding the right grade of PLA or something like that. So we'll talk about some of these unusual things that can be achieved with architecting. Thank you very much. I will see you on Zoom on Tuesday. Thanks a lot.
Thank you.
See ya. Thank you.
Thank you.